Okay, guys, welcome to Science Today. There is a video that I posted. It's in the classroom that goes with this unit, similar to the last one. It kind of explains nitrogen water cycle. So let's go ahead and dig in this a little bit. Okay, it says most of the Earth's water is in the oceans. Most of the nitrogen is a gas in the air. Living things both use water and nitrogen, which cycle between the Earth's surface and the atmosphere. Then we have nitrogen in the environment. most of the Earth's atmosphere is made of nitrogen gas, but most plants and animals need nitrogen in the form of nitrogen compounds in order to use it. During nitrogen fixation, nitrogen gas is changed into useful nitrogen compounds. Lightning helps with nitrogen fixation. The energy from lightning joins nitrogen and oxygen in the air. The new compounds mix with rainwater. Most nitrogen fixation is done by special bacteria that live in the soil, water, and on the roots of some plants. The roots feed the bacteria, and the bacteria give the plants fixed nitrogen. Organisms called decomposers keep plants and animals from using all the nitrogen. Decomposers such as bacteria and fungi break down or decompose animal waste, dead plants, and animals. This puts nitrogen compound back in the soil so plants can use them. Other bacteria change nitrogen in the soil into nitrogen gas in the air. So that means, when animals and plants die, they decompose, and that puts it in the soil. That's what that was talking about there. And so sometimes people do things that leave too much or too little nitrogen in the soil. This upsets the nitrogen cycle. When farmers cut down plants that are used for food, the nitrogen in the plants goes away and does not come back. Water can also wash nitrogen out of the soil. Farmers put chemicals called fertilizer in the soil to add nitrogen back in. They also use plant peanuts or beans because nitrogen-fixing bacteria live in their roots. So this is kind of basically the cycle I want you to, you can see nitrogen in the air goes into the soil, then solid nitrogen from the trees. Also, when this, I think that's a deer or maybe dies, it goes in the soil. And then the nitrogen comes out of the soil into a gas and it gets in the air. And that's how continually the nitrogen cycle works. Okay, it's in the air, goes into the ground, mixes with the plants, the dead animals, and then it comes back through the soil, back up in the air. And this is like a constant cycle. Okay. Now, it says the bodies of all living things are mostly made of water. I think our body is about 70 or 80% water. Living things need water so the life process can work, like oxygen and carbon dioxide. The water cycles through the environment. It said most of water is found in the oceans. Ocean water is salty. Fresh water is found in lakes, rivers, and bodies of water. So obviously by us, the Atlantic Ocean is salt water, but Lake Ontario is fresh water. Some of the water on land is under the ground in soil or space between solid rocks. Frozen water makes up snow, ice, and large pieces of snow and ice called glaciers. Water in the atmosphere is water vapor and tiny drops of water and ice clouds. Water is always moving from the Earth's surface to the Earth's atmosphere and back to the surface in a process called the water cycle. Energy from the sun heats up water in the oceans and on land. During evaporation, water uses this energy to change from a liquid to a gas called vapor. Similar, if you boil a pot of water, you heat it up, you can see the water vapor starting to come out of your pan on the stove. And this is kind of the same thing. The Earth would be like a giant burner, and it heats the water up, then water goes into vapor. It can come out of a lake, come out of a river, come out of a stream. It gets in the air. Then now it says water evaporates from plants' leaves during a process called transpiration. Animals are also part of the water cycle. They give off water as urine, sweat, as water vapor when they breathe. Any liquid water animals give off evaporates, just like our sweat evaporates too. It says water vapor in the atmosphere condense and can turn into a liquid. Tiny drops of water from clouds. When drops of water get heavy, they fall to earth as rain, sleet, hail, or snow. Water falls to earth from a cloud is called precipitation. That's like rain, like I said, snow, hail, sleet, whatever. Okay. It says about 3/4 of Earth's surface covered with water, but 97% of the Earth's water is salty ocean water. Only 1% of the water is usable fresh water. As the number of people on Earth grows, conserving water will become more and more important. Okay, so like it says, only 1% of the water in the world is fresh water. And the biggest source is the Great Lakes by us. You have Lake Ontario, Erie, Lake Michigan, Lake Superior. The 5 Great Lakes are all, Lake Huron would be the 5th, are all the largest sources of fresh water in the world. Okay. So most of the water that people use comes from water in rivers or lakes or from water that is stored underground. Some fresh water can be used because it's polluted by chemicals and metals that enter groundwater, rivers, and lakes. And it says deforestation or cutting down trees means less water vapor joins the water cycle through transpiration. This means fewer clouds and less precipitation, making these places drier. Okay, so what this is nitrogen water cycle. So these questions right here would be similar to what we just talked about. So you can go and just go back up to the reading and fill these out. I think there's maybe 10 or 11 of them, 12, and then there's 13, okay. Here are the answers right here, so you can check yourself. And this specifically deals with the nitrogen cycle, and you guys are familiar with this. You're just going to fill in these 2, 4, 6, 8, 10 vocabulary words with the proper one, and then the answers are right here. And then we're going to have we'll read this one right here. So there's a deep and complex relationship between living creatures, inorganic materials such as rock and minerals, and the climate conditions we experience, such as rain and wind. These relationships are not easy to see. Sometimes a relationship operates on a level that is microscopically small, such as when plants transform sunlight and nutrients. Other times, a relationship can be observed by across a hugely long span of time, hundreds, thousands, or even millions of years. But there is connection there, and we're in a unique, privileged position to see and appreciate it. If you could overcome these 2 limitations of everyday seeing, you can see things that are very small and subtle, and you can see things that occurred over a long stretch of time, what would you see? This says it's a matter of debate, but there's certainly a good case to be made that photosynthesis may be the most exciting process we know of. We know how plants are capable of converting water, carbon dioxide, and sunlight into oxygen. They're able to achieve this remarkably feat with a relatively small number of separate parts, and have done so very reliably for ages. So what this is saying, you guys, we can't really see when a plant takes in water, carbon dioxide, and sunlight and gives off oxygen, but we know that happens. We know that plants are basically giving off oxygen, and it's just like a process, and it's kind of hard to see, but we know it works, okay? Anyone who's ever had a household plant, watered it, sat near a light, watched it grow, and felt the air and home to be cleaner has experienced this magic firsthand. But if you can see the process, at a microscopic small scale, this abstract magic would be revealed as an extraordinary set of mechanisms. So what that's saying, if you have a house plant, you water it, you have in your window, it's going to grow. But not only is it growing, but it's giving off fresh oxygen. And it's kind of a process. It doesn't just happen like instantly. It takes time. And but the benefits are you're giving that fresh oxygen in your apartment or your house, okay? And then this next one says, excuse me, what if you could see photosynthesis working over a span of billions of years? This is the other remarkable thing. This mechanism, which operates on a small scale imaginable, has consequences that are literally global in scope and span ages. If you could watch the Earth evolve, you could see how over 2.5 billion years ago, before the emergence of plants, they could release oxygen. There simply wasn't much in it all the atmosphere. Not much oxygen in the atmosphere meant there were nowhere near the number of variety of creatures we've come to know today. Over the course of hundreds of millions of years, we're slowly seeing the emergence of tiny organisms capable of producing oxygen. However, you've noticed that most of the oxygen was captured by minerals and other organic matter, never growing to very high levels in the atmosphere. Sooner or later, these organic and inorganic matter would reach their saturation points, simply where they could not absorb any more oxygen. That's when the oxygen created by organisms become free oxygen for everyone. So obviously, trying to plant more and more trees, and obviously the Earth looked vastly different. Like it said, 2.5 millions of years ago, there weren't a lot of trees. Okay, but then it came to a point where everything on the planet at that time couldn't take any more oxygen, and that's when the oxygen started being released in the atmosphere, and that's where more things started to pop up. Okay. Then, as you observe across the age, you begin seeing the atmosphere change from one dominated by methane and other amounts to one plentiful oxygen. As we know, this is what set the stage for huge diversity of mineral and organic life to emerge, including many billions of years later, all human beings. All of us, along with the foods we consume and the ground we walk on, are the direct descendants of a process that began billions of years ago and continues today. All across the planet, on a microscopically small level, what could be more exciting than that? Of course, if photosynthesis is the most exciting process we enjoy, then energy from the opposite direction, heat from the Earth's core, is the most mysterious. That's because it originates, at least in part, from events that occurred from the very formation of the planet. Can you imagine such a thing as pre-Earth space? It's a pretty heavy concept, but imagine the part of the universe what the Earth would soon be yet. That's when the hot gases and particles will pull together by gravity, create the early Earth. Immense heat was generated, and the resulting planetary core continues to cool this day, radiating heat outward. The movements of more and more less dense parts of the Earth's core produce heat. Most of all, there are massive amounts of radioactive material deep in the Earth's core, decaying slow and releasing heat as they do. So part of that is, you guys can think about, I know in class we covered, like, when you see a volcano erupt, all that lava, there's hot gas, there's hot liquid, that's all coming from the Earth's core. That's what it's kind of talking about. And that's what really kind of formed, if you can think about, there's all these volcanoes underneath the sea. It shot all that hot lava up, and eventually the ocean cooled it. And that's really where our continents came from. So deep in the center of the Earth, it's really hot, and there's solid material, there's gas. Like when you see a volcano explode, not only do you see the lava coming out, but you see a lot of smoke and a lot of ash, and that's just gas being released too. This is why energy from the sun sends motion and extraordinary interaction between the atmosphere, organisms, and minerals. Energy from the Earth's core profoundly affects the shape on the ground we walk on. Literally, again, imagine you have the power to see a very small and very slow process that result from the Earth's energy to operate on all these levels. We're all familiar with the most visible results, earthquakes and volcanoes, which can be mighty indeed. But energy from the Earth's core is also responsible for the shift of tectonic plates. That is the very placement of one continent relative to another. As a result, the emergence of mountains, chasms, oceans, and more aspects of the environment. We covered this in class a little bit. I showed you a map of kind of the plate tectonics, and that's what really causes, like, our earthquakes and our volcanic eruptions. When the plates are on, it's almost like they're on skates a little bit, and they're constantly moving. And when they eventually collide, that's when you get like an earthquake, or you might get a volcano erupting. Okay, this is what it really means to contemplate the origins of the planet and the universe. It's not simply a matter of faraway cosmos relationship to the question how it came to be in events occurring unimaginably long ago and taking place at a rate so slow it's impossible to see, have come to shape the ground we walk on. The decay of radioactive material deep in the Earth's core is responsible not only for the Rocky Mountains, but the formation of cities and societies that have lived here for generations, such as Rocky Mountain National Park, which serves as a beacon of natural wonders to American Canada. It's responsible for mountains that serve as bringing life divisions to cultures unique in each side, while also posing a challenge to be crossed and burrowed, spurring on scientific innovation in the process. So, like, some mountains separate countries. Like in the Middle East too, there's mountains that really separate countries, and all that. Those mountains was just like hot material that come up through the ground. They form the mountains, and even they form the ground. That basically the ground we walk on is just hot lava that's been cooled. It has lots of different minerals and rocks in it. So many aspects of what it means to be human, from the way cities are constructed to the very nations are organized, are influenced by our national environment, by the vast and complex set of processes that have shaped the earth since its inception, and will continue to do so long into the future. Okay. And here are just some more questions from the reading. Once again, the answers are all right here. So really, the biggest thing I want you guys to take away from this, that last one just kind of gave you a big picture, because the earth is, really old, and it's really, a lot of those changes are really slow. But the thing I want to kind of focus on is this water cycle here. Pull this up. Right here. So this is the nitrogen cycle. Now this is important to kind of get a feel. You can see how the nitrogen is in the air, goes into the ground, and like I said, dead plants, roots, dead animals all get in the soil. Then eventually that nitrogen comes up to the ground, gets back in the air, and it's constantly, so the nitrogen is constantly moving from the air into the ground, back into the air. Okay, and that would really be the nitrogen cycle. And then the water cycle too, and you can see basically there's water in the air, there's water in the ground. The sun basically heats the water in lakes, rivers, it gets in the air. Then when there's enough precipitation in the air, those little water particles, when they get heavy enough or they group together, they fall in rain, snow, or sleet. So it's very similar to the nitrogen cycle. So both, you have to think, both nitrogen and water are constantly moving from the ground to the air, back into the ground, back into the air. It's constantly going on. Okay, guys, I'm going to start social studies here in about 10 minutes. I'll post this and you guys can watch the video. It'll give you a little background on both the water and nitrogen cycle. All right, you guys have a wonderful day. I'll talk to you soon.